Okay, next type of reaction we are going to look at is an elimination reaction. So far we've looked at combustion, where we were combining with oxygen to make CO2 and water, and we looked at addition, where we were starting with either an alkene or an alkyne, and we were adding a small molecule to it, and basically reducing that double or triple bond down to a single. So now we're looking at elimination. So elimination is basically the opposite of an addition. So what happens in an elimination, and why it's called an elimination, is that we are going to eliminate a small molecule. So if you think of when we did addition, we added a small molecule, it had two parts to it. So in elimination, we're going to eliminate a small molecule, which has two parts to it, and in doing so, we're then going to create a double bond between those two carbons, right? So if you look here, we have a molecule which has some hydrogens, and then it's got an A and it's got a B. So what's happening in elimination is that A and that B are both coming off, right? And they are forming that small molecule. And then what's happening is the carbon that sits here, as well as the carbon that sits here, becomes short one bond. So the way they fix that is they create a double bond in between them. This way, each of the carbons still has 1, 2, 3, 4 bonds, but one of them is now a double bond instead of two of those single bonds. So what small molecule you eliminate really comes down to what type of starting molecule did you have and what did you add to it. So one of the types of eliminations that we can have involves an alcohol. Okay, so in an alcohol, we're obviously looking for something to have that hydroxyl group, which you can see we have right here in this example. Okay, so what happens is, because we're doing elimination, this OH is going to come off. You think about some of the small molecules we talked about the other day. The one that involved OH was water, right? It was that HOH, which means we're going to have to take an H off from somewhere else. So we talked the other day about generally not kind of using line diagrams for reactions, and that's because it's kind of hard to see what's where. Definitely having those full structural diagrams does tend to make it a little bit more obvious. But we have an OH that's coming off of this carbon here, right? And although it's not indicated, we have a bend in the line, which implies that we also have a carbon sitting here. So for us to be able to create that double bond, right, by taking this OH off, either I have to create a double bond over here, or I have to create a double bond over here. For this particular molecule, it really doesn't matter where I choose to do it because it's going to wind up being the exact same thing. So in this case, we're going to take an H from this guy just so that it lines up with what we see over here. So again, it's kind of all compressed together, so it's a little bit hard to see, but we do have 3 hydrogens, right? So if you think about it, we have a hydrogen over here, one over here, and one over here. So to be able to ultimately create a double bond here, which is what we need to do in elimination, we have to take one of these hydrogens off, right? Otherwise, if we look at it, this carbon already has 1, 2, 3, 4 bonds, and it can't have more than that. So what we're going to do is we're going to take one of these, right? And I didn't write the H's in there, but there is technically a hydrogen there. And we are going to take that off, and it's going to go with this OH, and that's going to make our water, right? Even though we've written it as H2O, that's really the same as having written it as that HOH, right? Which is kind of how we were writing it when we were looking at the addition reactions. So in creating that water molecule and taking this OH away and this H, now this carbon has 1, 2, 3 bonds, and this carbon has 1, 2, but again, what's not shown is that other hydrogen hanging out over here, which makes it number 3. So to get them to 4, we're going to create a double bond over here, okay? So this particular type of reaction requires a catalyst, okay? And it requires a strong acid to be that catalyst. So in this example, I've used sulfuric acid, but remember, strong acids are any of the first 6 listed in your data booklet. So it literally could be any of those 6. Generally, it's written over the arrow. Sometimes it isn't. Sometimes it's actually written in the equation. But we would have to be able to recognize that when we have an alcohol in the presence, I guess I need to do that a different way, of whatever that strong acid is. I'm writing that over my arrow. that should have been black. Let me fix that real quick. So when we have an alcohol in the presence of a strong acid, that's going to be one of our options for elimination. And that's going to wind up producing alkene plus our water, okay? So the water, because an alcohol has that OH group in it, when we take that with H, that's where that water is coming from, okay? So that is one of the specific sets that work for elimination, right? So if you think about all the things we've talked about so far, we did combustion, which was a hydrocarbon plus oxygen. Then we did addition, which was an alkene or an alkyne plus a small molecule. Now we're looking at elimination. Okay, there's two eliminations we look at. This is the first one, which is an alcohol in the presence of a strong acid. So far everything is different, right? We don't have overlap, which is nice because it kind of makes it so that I can look at what my reactants are. I can decide what category they fall under, and then I can make sure that I'm actually doing the right reaction. So the second type of elimination is our alkyl halides. So these ones, what you're going to find is that halogen part is going to be what comes off. So one way to think of it, it's not the most technical, but if you think about when you want to do elimination, you have to have something special that you can take off, right? In the case of an alcohol, it's that hydroxyl group. In the case of an alkyl halide, it's that halogen. We're always going to be taking that off of one of the carbons, and then off the other one, we're going to be taking a hydrogen so that we can create that double bond, okay? So for an alkyl halide to be able to undergo elimination, this has to happen in the presence of a strong base. Okay, so alcohols need a strong acid, and alkyl halides need a strong base. So right here, right here is an example of a strong base. Okay, that's not generally one of the ones we talk about, right? Normally when we talk about strong bases, we are talking about group 1 and 2 hydroxides, right? So like sodium hydroxide, potassium hydroxide, barium hydroxide, those all count as strong bases. This guy here is known as sodium ethoxide. It is also considered to be a strong base, and you will sometimes see reactions that occur with that. And the last option that you will sometimes see is just to have that hydroxide ion present. It doesn't mean we don't have a cation. We do. It just kind of implies that it's our spectator of that reaction. Okay, so a little bit similar to the other type of elimination in that we are going to be creating a double bond, but a little bit different in that how we go about doing that changes a little bit, okay? So some parts stay the same, right? I talked about how you have that special thing that's going to come off. In the case of an alkyl halide, that special thing is your halogen. So in this case, this bromine is going to come off of the carbon that's here. But again, this carbon isn't drawn, but think of it as there's a carbon here, which has 2 hydrogens on it, okay? So when we add our strong base, what we are going to find is that the cation part of our strong base is always going to pair up with that halogen. So you can see here how the sodium went with the bromine over here to make that sodium bromide. Okay, the next thing that's going to happen is as this comes off, this carbon now goes down to having 1, 2, 3 bonds. But we need to be able to turn this right here into a double bond. The only way to do that is, again, this is all kind of written compressed, but if we pretended that those 3 hydrogens were all hanging out, is to take one of these away, right? And so where that hydrogen is going to go is with this oxygen here, right? Because technically hydrogen has a positive charge, this oxygen has a negative, and opposite charges attract each other, which is why when you look over here on the product side, you're going to see that it's HO, and then there's that same kind of part to that molecule, okay? So we're still creating a double bond. We just find in these molecules, we also have 2 other products. Okay, we have the sodium bromide in this case, which happened from the sodium from here, combining with the halogen in here. And then we have this molecule over here, which results from this part of the sodium ethoxide combining with that hydrogen, okay? So when we are looking at this one, we find that we have an alkyl halide with a strong base. So somewhere I'd probably suggest maybe like some flashcards or some cue cards, really helpful for organic, just so that you can kind of keep track of everything, but kind of have a list somewhere going so that you can kind of recognize what type of reactants mean what type of reactions, so that you can actually go about predicting that. Okay, so let's look at some examples. So the first one we have is propan 2-ol with sulfuric acid, okay? So prop means 3 carbons, right? So 1, 2, 3. Okay, it's a 2-ol, which means that off of carbon number 2, which is right here, we are going to have that hydroxyl group, right? We're going to have that OH. Okay, every other spot is going to be filled up with hydrogens, right? So we're going to have hydrogens in all of these other spots, right? Making sure, well, that line kind of came out longer than I meant to. Making sure that every carbon that we have has a total of 4 bonds associated with it, right? Because we talked about carbon always wanting 4 things attached to it. Okay, so we fill all this in. Okay, we are combining this with sulfuric acid. So this is where you need to start to be able to recognize what type of reaction something is going to be, excuse me, based off of what you're having, right? So I should be looking at this and I should be saying, okay, I have an alcohol. So let's think about the types of reactions we've talked about so far. We talked about combustion. Well, for this to be combustion, I need to be combining it with oxygen. I don't have oxygen, so it's not combustion. Then we talked about addition. We said for it to be addition, we had to have an alkene or an alkyne. We don't have any double or triple bonds, so it's not addition. So then I get to elimination. So elimination, we said either could be an alcohol or an alkyl halide. Well, we have an alcohol, so we're partway there. The next thing is we have sulfuric acid, right? So we have that last piece that we need, right? So in this case, I'm going to recognize that it's a catalyst, so I'm going to put it over my arrow, okay? So now what we're going to do is, now that we have decided that it is going to be an elimination, I have to know what that actually means, right? I have to know that elimination means I'm going to eliminate my special thing, which in this case is my hydroxyl group. So that's coming off of the central carbon. Then I need to eliminate an H, either off of the carbon on this side or off of the carbon on this side, right? It always has to be off of a carbon that's next to it. Sometimes people will be like, oh, Miss Chip, why can't I get rid of this one? So if I were to get rid of this one, and it wasn't there anymore, this carbon would still have 4 bonds. This carbon would also still have 4 bonds, so I wouldn't actually be able to fix it. Okay, that's why we either have to go to this carbon or this one, and in this case, because we only have 3 hydrogens, it really doesn't matter. Obviously, if I had more, I would have to worry about isomers. But in this example, I don't have to. So I'm going to choose to take that hydrogen off. So in taking those 2 off, we are going to create our small molecule, which is going to be that water. And then by removing this and this, right, if you think about what we now have, right, we still have that same starting molecule, but we're going to get rid of that H. And okay, so we've gotten rid of the H and the OH, right? Now it looks exactly the same as it did before. We've just eliminated those 2 sets to create the water. So now when I look at it, this carbon, if I look, it only has 1, 2, 3 bonds, so it's missing 1. I look at the next carbon over and it's in the exact same situation. It also only has 3 bonds. So how we're going to fix that? Instead of having a single bond here, we're going to turn that into a double bond. Okay, so now when we look at it, this carbon now is back to having 4 bonds, and this carbon is also back to having 4 bonds. This one we never touched anything about it, so it's still at 4 bonds. Okay, we need to name this. It's a prop because we have 3 carbons. It now has that double bond, so it's going to be an ene. Normally we would want to put a number in here, but in this case, it doesn't matter if I chose to put the double bond over here or if I chose to put it over here. It would still technically be in the exact same spot. It would just be a rotated image. So when we find that we get the exact same thing, even if we flip it around, we do not actually need to include a number in that formula. Okay, so here's another one for you to try. We have bromoethane plus that sodium methoxide. So a quick, I don't want to say hint, but anytime you see sodium methoxide, that has to be elimination. It doesn't get used in any other types of reactions. So if you see it, I wouldn't even bother really thinking, oh, could it be this or could it be that? That sodium methoxide absolutely has to be elimination. There is no other option of what it's going to be. Okay, so bromoethane. So we have eth, that is 2 carbons. Single bond because it's ending with ane. It says bromo. There's only 1 because there's no di or tri or tetra. There's no number though, and that's because it really doesn't matter which one of these carbons I put it on, it's the exact same thing. So I'm just going to put it in at the beginning, but you got to put it on the second one, it really doesn't matter. And then we are going to fill in the rest of this molecule so that it's a complete molecule, right? We're going to do that by adding those hydrogens in that we need to have. Okay, and then do the same thing on the bottom ones. Okay, so now I have my bromoethane. Okay, we are going to combine that with this sodium methoxide. Just copy paste that, so I don't have to type that whole thing in again. Okay, so a couple of ways. Either I'm going to recognize its elimination because I have sodium methoxide, or I'm going to go through that little mental checklist like we did with the last one, right? Not combustion because there's no plus O2. Not addition because I don't have any double bonds. And then we get to elimination, we're going to say, oh, I have an alkyl halide. Do I have a strong base? Yes, I do. This is going to wind up being elimination, okay? So when we look at this, we know we're going to take the bromine off. Okay, the bromine is going to go with the sodium, right? So those are going to go together to create sodium bromide. Okay, then we need to take an H off, right? Because otherwise we can't actually create that double bond. So can't be off the same carbon I took the bromine off of, has to be off the next one over. So I could take either of these 3, really doesn't matter. I'm going to choose to take this one, and that's going to get paired up with all of this. Okay, so then down here, we're going to have the next part of this molecule is OH, or HO, sorry, CH2, CH3. Okay, now we have to actually put in this organic molecule. So we've now taken the bromine off, so it's not there anymore. So we have the carbon going to that other carbon, which had its hydrogen. We then have the hydrogen that's up here, and then we have the 2 that are down here, right? And I'm not drawing the others because we took them off. When we did elimination, we removed those. Okay, so an H here, and we have our H's down here. Okay, so now when we have a look at this, this carbon has 1, 2, 3 bonds. It needs another one. Look at this one, 1, 2, 3, it also needs another one. So we're going to fix that by, instead of drawing a single bond, we are going to draw a double bond. Okay, so now when we look at this, we've got 2 carbons, each has a total of 4 bonds, and we have just made ethene. Okay, and again, we don't need a number. There's only 2 carbons, so there's only 1 spot for that double bond to go, and that is smack dab in between the 2 of them. Okay, so that is your elimination.